Hello guys, welcome back to Math with Amala. Let's move to the part 7 of grade 9 chapter 1. Here we are dealing with real numbers and decimal expansions. Actually, we have done some portions regarding the chapter 1. So please do refer the description for the previous links. Real numbers and their decimal expansions. What are real numbers? We have discussed already about the rational, irrationals and their combination real numbers. Let's take some numbers like 10 by 3, 7 by 8 and 1 by 7. Let's divide it with the usual uh, procedure. The normal division method. 10 by 3. 10, how many 3s are there in 10? 3 3s into 9 into 3, that is 9. Remainder 1. Then again you can put the decimal and put 0. Then 3 3s are 9, remainder 1. So it goes like 3.33333. It doesn't end. It goes with the remainder 1. Next is 7 by 8. You can continue like this with the 64, 56, 40 and you will get the quotient like 0.875 and the remainder is 0. Next is 1 divided by 7. 0.1 sevens are 7, then 30, then 4 sevens are 28, then 20, then you can take 2 sevens are 14, that is you will get like remainder 6 and you can put a 0 over there. Then 8 sevens are 56 and it goes like that, like 0.142857, it goes like that, which means it is not ending, it is recurring. You can say, you can use the word recurring. So in the first case, the remainder was only 1, nothing else. In the second case, 0 was there. So the division was terminating there. It was not recurring. But then in the last one, it is not ending at any point. It is going with some other points and it continues. So we are having two cases here. Case 1 is terminating case. That is, you are getting the remainder as 0 and the division stops there. Case 2 is remainder is never getting 0. So the case 2 is having two cases like the first one and the third one. Case 2 is remainder never 0. Remainder is never 0. We have an example number 6, which is to prove, actually it is an example means we have to show it like 3.142678 is belonging to Q. This is the value of pi. Belongs to Q means we have to represent this in the form P by Q, that is an integer divided by an integer, and Q is not equal to 0. Here according to the number of decimal places we can give the multiples of 10 on the denominator. So the representation is very simple. Now let's move to the example number 7. 0.333, it is actually we can represent like 0.3 bar. That means if any number is with the bar on the upper side, then you can read it like that number is repeating. So P by Q form, we have to represent this also in the P by Q form. So 0.12 is with the bar means that 12 is repeating. 0.123 is repeating means 0.123, 123, 123. Now let's take that x equal to 0.333 etc. Okay. Now in order to get a solution, we are multiplying that x with 10. You will get 3.33 which is equal to 3 plus the first x. Now let's take 10x minus x which is 9x which is equal to 3, which implies x equal to 3 by 9, that is 1 by 3. Next, the 8th example, 1.2727 etc. which is equal to 1.27 bar. Bar is on 27 in the form P by Q. X equal to 1.2727 etc. Then we have to place 2 places towards the right. That decimal should be placed towards 2 places towards right. That means you have to multiply that number with 100, not 10. 100x equal to 127.27 etc. 100x equal to 126 plus 1.2727, that is 126 plus x. 100x minus x is equal to 126. 99x equal to 126. X equal to 126 divided by 99, which is equal to, we can shorten it like, simplify it like 14 by 11. That 14 by 11 is actually 1.27 bar. Okay. This is the answer for the P by Q form is 14 by 11. P is 14 and Q is 11. Ninth example, 0.235 which is equal to 0.2. 35 is only having the bar because only 35 is repeating, 2 is not repeating there. Let's take the first number as x. So 100x equal to 23.100x. We have to place the decimal towards 2 places towards the right. So 23.53535, 23.3 plus 0.23535 which is equal to 23.3 plus x. 99x equal to 23.3. Now we can represent that 23.3 in terms with the multiplications of division of 10's multiple, that is 10 into 1. X equal to 233 by 990 which is equal to 0.235 bar. Okay, 35 bar. Generally we can say like decimal expansion of a rational number is either terminating or recurring, and also a number whose decimal expansion is terminating or non-recurring, not terminating, is a rational. Okay, so the vice versa is also true. Thus any number in the P by Q form can be expressed in decimal expansion forms, and also the decimal expansion will be working for the rational numbers. So these general cases can be used in order to find a particular P by Q form rational number for some decimal expansions. So rational numbers which are in the form P by Q can be will be having a decimal expansion which can be terminating or recurring, and the vice versa. This is true for irrational numbers when it is non-terminating and non-recurring, and the vice versa also. Let us take the root 2 value. Root 2 is equal to 1.4142 135623730950488016888. Also the pi value is 22 by 7 which is the P by Q form, and which is approximately equal to 3.14, and we have given some places, decimal places here. That means whatever be the decimal points or whatever be the recurring condition, there will be a particular P by Q form or the rational form for the number, or it can be an irrational form for like the root 2. Okay, so we will be approximating that value to some particular points. The number of decimal places in the pi value is getting increased from ancient to modern times. Archimedes found that pi value is lying in between 3.140845 and 3.42857. And then Aryabhatta found the value for up to 4 decimal places, 3.1416. In the modern scenario, this value changed to a record with 1.24 trillion decimal places. So this is the value of pi right now. Thank you all for watching the video. Please be stay tuned and clear your doubts through comments.